All right, ladies and gentlemen. So perhaps you were absent, or perhaps you just want to go back and have another look at this particular topic. But we are looking at the properties of ionic compounds like you saw in the laboratory that we did in class. All right, so ionic compounds are solids, as you saw with the white powder that we, or the white granules that we had in class, and they have high melting and boiling points, which is why they did not melt when you put the heat under them. All right, now remember, ionic compounds are made of two things. They are made of cations. Those are positively charged, and they are almost always metals, right? So you'll have a positive and a positive and a positive and a positive and a positive. And they are made of anions, which are negatively charged, and they are nonmetals. And so you got a negative and a negative and a negative and a negative. All right? So what happens is you have between any positive and negative charge. So let's just take those two right there as an example. So between those two, that positive and negative charge have an attraction. They attract one another. Now, because it is an attraction between a positive and a negative, the chemical name for it is an electrostatic attraction. Electro meaning positive negative, transfer of electrons. Static doesn't move. So that positive and negative are permanent. They are attracted to one another. That electrostatic attraction between those anions and cations. Because any ionic compound is made up of billions and billions of ions, the electrostatic attractions between the positive cation, actually I should say cations, shouldn't I? And the negative anions is very strong. So they are always solid at room temperature, of course, and have high melting points. Which I will often abbreviate as temperature of melting. Okay? Now, how can you judge the strength of the bond? Well, there's several ways, but the one that they cover in the book is you measure the strength of the bond is related to the electronegativity difference. Okay? So I've got two compounds here, sodium chloride and sodium iodide. So what I'm going to do is I'm going to go to my electronegativity table, and I'm going to find sodium, and the electronegativity is 0.93, and chloride, and the electronegativity is 3.16. So I've got a 0.93 and I've got a 3.16. So the absolute value of the difference between them, okay? So 3.16 minus 0.93, the electronegativity difference is 2.23, okay? So then I do the same thing for sodium iodide. Well, clearly it's still sodium, right? So 0.93, but I need to look up iodine. Well, the iodine electronegativity is 2.66. I do that difference, 2.66 minus 0.93, and I get 1.73. So the strength of the sodium chloride bond is greater than the strength of the sodium iodide bond. All right, well, how can you test that? Well, there's any number of ways that you can test it, but one of my personal favorites is we can simply look up the melting points. So, melting point for sodium chloride is 801 degrees Celsius. So, temperature melting, 801 degrees Celsius. Well, then we can do the same thing for sodium iodide. Melting point, sodium iodide is 661 degrees Celsius. So the temperature of the melting point is 661 degrees Celsius. Clearly, this one melts at a lower temperature than this one, so the strength of the sodium chloride bond is more than the strength of the sodium iodide bond. And you can judge that with electronegativity difference. All right. Then you found out that if you take the ionic compounds and you put them in water and you stirred them up, that they dissolved. Okay? And so when they dissolved, what happened was all of these positive and negative anions and cations, they broke apart, and so they are still there. All right, so we had 1, 2, 3, 4, 5 cations in that diagram. So we have 1, 2, 3, 4, 5 cations, and then we have the rest of them are anions. There we go. And all of the rest of this is just water molecules, right? Everywhere, water molecules. Right? So we are surrounded by water. All right. H2O liquid. All right. So that breaking apart that they do, that is what we call dissolving, right? They are dissolving. Now, then you put in the conductivity probes. So we put in a probe here, a probe here. It had a battery, and it had a little light bulb. And when the whole thing, and when you you stuck it into the solution, the little light bulb lit up, right? And so that was telling us that it conducted electricity, right? So that tells us that it conducted. All right? Now, so ionic compounds conduct electricity when they are dissolved in water. Now, the reason for that is that these ions right here, the positive ones are constantly kind of trying to go towards the negative electrode, and the negative ones are constantly kind of trying to go towards the positive electrode. And so these positive and negative ions are moving all the time through the solution. That is what conducts electricity. So, ionic compounds conduct electricity in solution. That's a solution. In other words, when they are dissolved, because the moving ions carry the electrical charge. And that is why they will only conduct electricity when they are dissolved like that. If you took that exact same thing and you put it up into the solid, right? So if you were to take the conductivity probe and you were to stick it into the solid with the same battery and the same light, then you would find that it does not light up, does not conduct electricity. And of course, that's what you found in the laboratory as well. All right. Finally, ionic compounds are very brittle. They break easily when you strike them with a hammer, okay? The reason ionic compounds are strong is because that positive is attracted to that negative, that positive to that negative, that positive to that negative. So you have that electrostatic attraction. If you hit them with a hammer, though, then something odd occurs. This is exactly the same as it was in the beginning, okay? So notice I would have blue, green, blue, right? Positive, negative, positive. And up here, positive, negative, positive, right? But if I hit them with a hammer, then what happens is the force of the hammer okay, so this is a force going into the thing. It basically forces the ions to kind of offset. It forces them down. And when that happens, you don't have a positive and a negative lined up on each other for an attraction. You have a positive and a positive and a negative and a negative, and these repel each other. And so here you don't get an attraction, you get a repulsion. And so the whole thing just fractures and breaks apart. Okay, so the explanation for that is when struck, like charged ions, in other words, positive and positive, and negative and negative, line up and repel, so the crystal breaks. And that is what we call being brittle. Breaks apart. And there you are. Those are your properties of ionic compounds.